In this set of videos, we're going to study strong induction. Like regular induction, the math induction that we've learned so far, strong induction is a proof technique for proving statements of the form for all n greater than or equal to some base n naught, some proposition p of n is true. So far, we've learned about standard, or sometimes now called weak, mathematical induction. So in standard or weak induction, what we do in the inductive step is to show that for all k greater than or equal to the base case n naught, p of k implies p of k plus 1. So this is our standard math induction approach to the inductive step. And when we do this, the base case, we just have to prove the base case for n naught, and that's it, we're done. Now, when we do strong induction, we give ourselves more information in the inductive step. There are two flavors of strong induction that I want to share with you. And in this video, we're going to focus on just one, and we'll introduce the other one in the next video. So the next flavor of induction that we're going to look at, strong induction, what we do is we say, okay, I want to prove p of k plus 1. My inductive step is still going to involve proving p of k plus 1, but I'm going to look back farther than just to the previous p of k. I'm also going to look back to p of k minus 1, p of k minus 2, and so on. And together, these many propositions are going to give me the information I need to derive that p of k plus 1 is true. So in our first flavor of this approach, our first type of strong induction, we're going to consider bounded strong induction. So bounded strong induction is where I assume a finite number of these previous p of k's to be true. And I'm going to use those in order to derive p of k. So what does this look like? When I do bounded strong induction in the inductive step, what I show is that for all k greater than or equal to n naught, that part is the same. And now what I'm going to do is I'm going to look at a whole collection of previous p of k's that are going to together imply p of k plus 1. So I still want to imply p of k plus 1, but in order to do it, I'm going to consider, I'm going to look back farther than just one step. So here in what I'm writing, I'm going to look back a total of a steps. So I have here a lot of different propositions, all the way up to p of k minus 1 and p of k. So what I'm saying here is that if I assume all of these things, p of k minus 1, p of k minus 2, p of k minus 3, all the way back here to p of k minus a plus 1, and the reason it's k minus a plus 1 is that I've tried to tune this in order to have a total of a propositions. That's how many are being assumed in this inductive step. If I can assume all a of those propositions, then I will be able to derive p of k plus 1. So I get, in some ways, an easier inductive step because I give myself more information with which to derive the conclusion. On the other hand, there is a cost to this. If I'm going to do bounded strong induction with a propositions in my inductive hypothesis, I need to use, in this approach, I need to derive a base cases. If I'm going to use bounded strong induction with looking backwards with the information from a propositions, I need to do a base cases. So the amount of work that I need to do in the base case goes up, even though often, not always, but often the amount of work I need to do in the inductive step goes down. So let's look at an example. Let's look at a problem that requires us to use bounded strong induction. So this is often called a postage stamp problem. So here's the theorem we're going to prove. Suppose that I have an infinite supply of 4-cent and 5-cent postage stamps. Yes, believe it or not, postage used to be on the order of 4 or 5 cents once. So suppose that I have some 4 cents and 5-cent postage stamps. Then claim from these stamps I can assemble any integer amount of postage greater than or equal to 12. So my theorem is not guaranteeing that I can create 11 cents worth of postage, but it is saying if I want to create 12 cents or more worth of postage, yes, I can do that just by building with 4-cent and 5-cent postage stamps. So let's look at a few examples of this. What the theorem is telling me is possible. Okay, so let's look at a few examples here. So if I consider something like 11, okay, 11 is not equal to anything, any combination of 4s and 5s. I can't do it. The theorem is not guaranteeing that for me. On the other hand, if I, let's make that a big angry X. On the other hand, if I consider 12, well, how can I make 12 out of 4s and 5s? One way is 4 plus 4 plus 4. What about 13? Well, one way to make 13, I can do 5 plus 4 plus 4. To do 14, I can do 5 plus 5 plus 4. To do 15, I can do 5 plus 5 plus 5. 16. Okay, so now when I do 16, I say, oh, I can do 4 plus 4 plus 4 plus 4. 17, this is going to be the last one. 5 plus 4 plus 4 plus 4. And so on. So my theorem is telling me that I can do this for any number greater than or equal to 12. So not necessarily 11. Let's go ahead and even just erase that. Not necessarily 11, but anything greater than or equal to 12, I'm always guaranteed to be able to do it. So when we think about proving this theorem, we probably want to look at these constructions and ask ourselves, hey, from these constructions, what's the insight here? What's the idea? What's, if you will, the algorithm that would allow me to, for example, construct 17? And this is where it's good to kind of look for patterns and relationships between what our constructions say. Here, for example, there's a useful pattern to notice, which is that if I look at 16, for example, if I look at 16, 4 plus 4 plus 4 plus 4, well, 16, that's actually just the pattern for 12 with another 4 added. Similarly, the pattern for 17 is just the same as the pattern for 13 with another 4 added. I can always add 4. And so if I can look back 4 steps and construct that, I'll be able to construct the number I'm on right now. So this gives us our big idea, which is the following idea. If we are trying to construct the integer k plus 1, then construct instead the integer k minus 3 and then add 4. That's our idea here. If I want to make k plus 1, I'll instead construct k minus 3 and then add 4 to it. So here, for example, if I want to construct 17, that's my k plus 1. K minus 3, in this case, would be 13, and then I'll add 4 and get the 17 that I'm targeting. So this gives us a question. If I'm going to do this, how many base cases do I need to do to make this work? How many base cases do I need? I'm going to let you think about that for a moment. So this is an example of bounded strong induction where we need to look backwards from k plus 1 to k minus 3, and that's 4 steps backwards. 4 steps backwards. So if k plus 1 is over here, k minus 1, k minus 2, k minus 3. So if we're starting at k plus 1, that's what we want to prove. We need to go 1, 2, 3, 4 steps backwards. So we are trying to go 4 steps backwards, which means that we are going to need to prove 4 base cases. Now, fortunately for us, we've actually already done it right here, and I'll say more about that, what that means when we actually get to the proof coming up. So let's go ahead and prove this postage stamp theorem. Suppose that I have an infinite supply of 4-cent and 5-cent postage stamps. Then I can assemble any integer amount of postage n greater than or equal to 12. So we're going to do this with bounded strong induction. And as we saw from kind of playing around in the last slide, the way we're going to do bounded strong induction, we're going to look 4 steps back, 4 steps. So let's go ahead and look at our base case. And the beautiful thing about some of the messing around we did is that we have actually already proven our base case. Here it is. For our base case, we're going to start at the smallest number guaranteed by the theorem. So we definitely have to do 12. Then we have to do 13, 14, and 15. And here's all those constructions. Here's those 4 constructions, and we know it has to be 4 constructions because we know that we have to look back 4 steps in the inductive step. So now writing the inductive step is just a little bit more challenging, but because we've done a lot of work in the base case already, we've done 4 base cases, the inductive step is actually also not too complicated. So let's go. We're going to suppose that p of k minus 3, p of k minus 2, p of k minus 1, and p of k are all true. Now, in this case, this is a slightly unusual case of bounded strong induction. I'm really going to be focusing on p k minus 3. I'm not even going to need the other ones so much. Regardless, what we're going to do is we will prove that p of k plus 1 is true. And in all of this, we are assuming that k is greater than or equal to n naught, which is 12. Okay, so if k plus 1 is less than or equal to 15, it's covered by a base case. So assume that k plus 1 is greater than or equal to 16. Then we can write k plus 1 is equal to 4 plus k minus 3, where k minus 3 is guaranteed to satisfy k minus 3 is greater than or equal to 12. If k plus 1 is greater than or equal to 16, and I subtract 4, I get k minus 3. That must always be greater than or equal to 12. We know by the inductive hypothesis that p of k minus 3 is true, i.e., k minus 3 is constructible. in terms of 4 and 5 cent postage stamps. So adding a 4 as specified by this equation, k plus 1 is 4 plus k minus 3, adding a 4 gives a construction for p, oh, sorry, not p, just k plus 1. And therefore, k plus 1 is constructible as well. That's what we wanted to show. We wanted to show that assuming these 4 statements in our inductive hypothesis would allow us to prove that p of k plus 1 is true. And indeed, we got there, and so we are done with our proof by bounded strong induction.